at the end, yeah. Oh. No.
Maybe?
There. Is the mic on?
Should be.
I'll take it.
Yeah, it's on.
Hello.
Maybe?
Go for it.
Welcome everybody to SpaceDrafts number 73. SpaceDrafts is Tucson's own version of the International Astronomy on Tap initiative of bringing astronomy to the masses through fun talks in low-key casual environments like this. We have two great talks for you tonight. We have John Barentine is going to talk about one of astronomy's oldest unsolved mysteries, and Kevin Hainline is going to talk about JWST Space Telescope and what it's been up to since Christmas. So my name's Tim. I'm your host and MC tonight. I work here in Tucson at the MMT Observatory, and we have I'm one of 5 of us here that help coordinate and bring SpaceDrafts here every month. So we will have 2 talks. There will be a 20-minute intermission between the talks, and during each talk we will have a trivia question, and if you have an answer, please raise your hand, and if you're correct, we have some prizes up here you can choose from. We have an exciting new addition this month. We now have a tip jar. Woo! And we had some stickers available for sale for $2 a piece. We encourage you to buy stickers because the more swag we can sell, the more new swag we can buy to sell, like pint glasses and stuff. So we heavily encourage tips and swag. What else?
Trains.
So we're by the trains here. So a tradition is when the talk is interrupted by the train, we will have to pause because you can't speak over the train. And so everyone will raise their glass and go, choo choo.
Choo choo.
What else am I forgetting?
Ticket margin?
I think.
I don't know. I think that's it.
I think. All right. Well, without any further ado, I will hand the mic over to Kevin to bring us up to date.
Do you want to introduce?
Let's not do that. Hi everybody. Oh man, where's my clicker?
Oh,
Here it is. I'm really excited to talk with you all because I just got back from Baltimore on Friday, where I was helping with this thing, which actually, for the first time in the time that I've been able to give talks about it, is in space. And so if you have never heard of this, welcome to, this is the thing, tonight is going to be all about you doing just that, because I do not plan on giving a very scientific talk. I'm going to give what I'm calling a victory lap, because I've done a lot of work. A lot of the people here at University of Arizona have done a lot of work, and it's very exciting about that. So that's what we're going to talk about tonight. I need to walk away from the old speaker. Or we should turn the volume down or turn the speaker that way or something. Thank you. So my name is Kevin Hainline. I'm a JWST NearCam project scientist. Talk about what JWST is in a second. I'll definitely talk about what NearCam is in a second. I'm here at the University of Arizona. I've been here for about 6 years. And tonight, as I said, we're going to do a victory lap, meaning that tonight I'm going to give a talk. This is my first time I've been able to give a talk where I get to do this thing, so you're very lucky. So what I'm going to do is I'm going to talk, and then I'm going to drink, and then I'm going to talk, and I'm going to drink, and you guys are going to cheer whenever you want, because there's a lot of very cheerable things that happen in this talk, right? Oh, thank you. I wish I could like beam the feelings that you're giving me back to all the people working on this, because there are people who are currently on shift right now. I'm not. I'm here. And they would love it if they could have a beer and listen to people cheer about this very exciting thing. So this right here is JWST. That's how I'm going to refer to it. It's the, I was just in Baltimore, it's the John Waters Space Telescope. It is a space telescope that has been in development for a little while, and it is, this mirror right here is about the size of an adult giraffe. Like, it's about 3.5 Shaquille O'Neals stacked on top of each other. It's the size of George Washington's nose on Mount Rushmore. It's pretty big. It's gold plated with these 18 hexagonal mirror segments, and it's NASA's Great Space Observatory. And for the entirety of the time that I've talked about it up to today, it has been a thing that I've talked about as a hypothetical. It existed, but it didn't exist in space yet. It's sitting on this sun shield here, which is a tennis court size. Just to give you an idea, you could park it right here in this patio, and it would be this enormous thing that would take up the whole patio. That's how big this thing is. It's really very big, and especially compared with poor little Hubble here. This is Hubble, the size of like a school bus. You're such a jerk, microphone cord. Okay, a little bit more. It's school bus sized. Sorry, everyone in the live stream.
I'll fix you.
Thank you. And its mirror is, about Shaquille O'Neal sized, and JWST's mirror is much larger, right? And with telescopes, the bigger the telescope mirror, the better the telescope's resolution, the more light it can capture every second. It's really amazing. And JWST is a telescope that will be working at the same time as Hubble is working, and so they'll work together. Hubble operates in the optical and the ultraviolet and a little bit into the infrared. Optical is what we see with our eyes. Ultraviolet is what we block with sunglasses. It's more energetic light. And infrared is the light of things that are warm and glowing because they're warm. It's just a little longer than optical light. JWST is entirely an infrared telescope. It operates well outside of the wavelength range that Hubble did. So they'll work together. They're very complementary, except one's way bigger. And the reason why I work here is because I work on one of the 4 instruments that are on JWST. So these are the 4 instruments. There's NIRCam, which was built here at the University of Arizona by the people at the University of Arizona, and also Lockheed Martin. I guess it was built at Lockheed Martin, but with, it was designed and built at the University of Arizona project. I'll talk about that more later. But there's also NIRSpec, which is a European instrument. There's MIRI, which is an American and European instrument. And there's NIRIS, which is a Canadian instrument. And when I say instruments, I mean what JWST is. It's like a big lens, like you'd have on a camera. But you can't just buy a lens and go, I see what I see. You need the camera body, like a DSLR or whatever. And these are the camera bodies. These are the things that actually take the light from space and turn it into electricity that we can then observe and see. NIRCam is an imager. It takes pictures of space, like what you'd expect. NIRSpec takes light and passes it through fancy prisms, so it can look at light as a function of its wavelength, which is very important if you want to understand the chemical makeup of things in space. It's a very, very fancy way of doing that. MIRI is kind of an imager and a spectrograph, so it does both of the things I just said, but it operates at a longer wavelength range. MIRI is a very, very important instrument. When I asked Marcia, my boss, Marcia Ricci, who's the primary investigator on NIRCam, meaning she is Miss NIRCam, she's the NIRCam person, what's the most important instrument on the telescope? She said, without any hesitation, MIRI. Because while NIRCam and NIRSpec have been things we've been able to do from the ground and from space slightly, MIRI totally opens up a new avenue in terms of its resolution and its wavelength range. Really very important instrument. NIRIS is another instrument on the telescope. It was built by the Canadians. It is a slitless spectrograph, so it kind of combines what these two instruments do. If you wanted to look at a bunch of galaxies in the sky at once and take their fingerprints, like with NIRSpec, you'd use NIRIS. But I don't talk much about NIRIS because I'm very biased towards NIRCam. This is what happens when you work on an instrument for many, many years, is you stop thinking about other instruments. So this is NIRCam. What I like about this image is it shows off the cool thing about NIRCam, which is that when Marcia and her team designed NIRCam, she said, why make one when you can make 2 for twice the price? And you can actually see that everything here is reflected down here, right? This box here is that box. You can see the curve on the other side, the pick-off mirrors. There's 2, I'm using my shadow now. There's 2 pick-off mirrors. It's in fact 2 modules that are identical. Well, they're mirror images of each other. Module A and Module B, and they have all the same innards. And so what NIRCam can do is take a big rectangular image, so 2 kind of squarish images next to each other. And in fact, what's cool about NIRCam also is that inside of NIRCam, there's a special thing we call a dichroic beam splitter, which is a very fancy way for saying that when the light comes into the telescope, there's like a bouncer that says, short wavelength, you go over there. Long wavelength, you go over there. And so at the same time, NIRCam can take a short wavelength image and a long wavelength image, and then it can take 2, because it has 2 modules, So there's a lot of data that comes down from JWST at once, from NearCam specifically. Big rectangular images and short and long wavelength at the same time, which means that NearCam is like going to be an incredible instrument if you're a person who wants, hey Siri, quiet, who wants to do, if you want to do a lot of science, but you don't have a lot of time, you want to look at big images in the sky, and you want to go like, I don't want to put a new filter in, I want to just take this image, then take another image a little bit later, or take another image with a different filter. You can actually use the beam splitter in that way, which is very cool. So every time I've given a talk, actually, here's my pop quiz. All right, I just want to do a pop quiz. This will help set the stage. Here's your pop quiz. Okay, so this is the quiz portion. When did NASA first start seriously thinking about a next generation space telescope to succeed Hubble? When? I want a year. All right. So think about it. I'll tell you. I got the job in 2015, so it was before then. So I see it way in the back. 91, good answer, but incorrect. Right here. 87, also incorrect. We're getting closer, though.
85.
Nope, 80, right here. 89 is, in fact, when the workshop, the next generation of 10-meter class UV visible IR successor to Hubble happened. And 1989, incorrect. It was, in fact, 1989. September of 1989. So you were very close, 91. The thing is 91 was the launch of Hubble, and it was in fact before Hubble launched that they thought, all right, we got this thing out the door, let's make a cheaper one. That's bigger. It'll be so easy, we'll have it out in 5 years. They were wrong on every account.
5 years. Oh.
This is a image from the workshop, like the book that came out with the workshop, showing like Hubble after 3 orbits of a galaxy, and then what this next generation space telescope will look like after 2 hours. And you know what? They actually did pretty well. It ends up being that the 10 meters was a little bit ambitious. They had to scale it down. The history of JWST, which you can find at this horrible URL right here, is fascinating because it's a history of a bunch of scientists who are very optimistic up against people who make budgets who say, you can't be that optimistic. And then they go, well, we'd like to be that optimistic. And then they say, well, you don't get a telescope then. And then they go to the government and they say, well, the government, you guys are going to stop funding our telescope. And they go, yeah. And they go, well, what can we do? You can name it after this guy. And then they do. And then there's like all these, it's a real long history. But in the end, this is where all of my talks had to stop, right? Oh, by the way, I love this. This is some images of JWST. I put this in at the last minute, which is why I forgot about it. Images of what JWST could have looked like over the years. And I love this kind of pie in the sky approach of like, what if we had a mirror that like looked crazy? Like, what is this? Like these crazy mirrors that are, you know, you can start seeing though that at least a few kind of had the idea. But also notice something, every one of these had this weird parasol attached to it. And that parasol is because JWST is an infrared telescope and it has to be very, very cold. Very, very cold. Colder than space. It has to be cold because if you're just floating in space, the sun is hitting you, which actually keeps you pretty hot. And so if you put a parasol, you're in the shadow from the sun, and then you can be very cold. And so that's what these parasols are on JWST. We call it the sun shield, and it takes the temperature from a couple 100 degrees Fahrenheit down to like, gosh, 40 degrees Fahrenheit. You know, very, very, very cold. 40 degrees Kelvin, excuse me. Sorry. Down to like 87? No, down to 40 Kelvin, which is very, very, very cold. So negative a couple 100 degrees Fahrenheit. And it was always part of this because if you build an infrared telescope, infrared things, like infrared is light from things that are warm, and if your telescope is warm at all, it will give off its own infrared light, and if you pick that up with your detector, you're only going to be taking pictures of the inside of your camera. You don't want pictures of the inside of your camera. You want pictures of space. You want the camera itself to be so cold it doesn't give off any extra light. And so that's why you have all these. So all these designs had that aspect. So anyway, up until tonight, every talk had to end with, get ready. Let's hope. Hope it doesn't blow up. And I had to start actually realizing that my job was going to really change when they took the telescope, which had been assembled at Goddard Space Flight Center in Baltimore and then finally put all together at Northrop Grumman's Aerospace Systems outside of LA, in LA, right outside of LAX. They put the mirror on the sun shield, they tested it all. A bunch of delays, they shook the telescope once and a bunch of bolts fell out of the telescope and they're like, that's bad, we shouldn't have that happen. So they counted all the bolts and said, we counted all the right bolts and we fixed the problem. and this caused delays. And then eventually, and again, when enough of these delays happen, you stop believing. And that's bad if you work on the telescope. But I stopped believing, and then in October of last year, they put the whole thing on a boat. This is a fun story. They put it on a boat. Marcia tells us all. They're going to put it on a boat at Long Beach Harbor, and you're not going to know what's going to happen. Because they don't want the public to know, because pirates could steal your telescope. The Atlantic, the August publication, The Atlantic, wrote an article last year, 2 years ago, saying, what if pirates steal JWST? And I was like, don't give them any ideas. And so Marcia said, to combat piracy, it will have an armed guard, but also you'll never know when it launches. So then when it launched, a bunch of people on Twitter are like, this is the boat. It has a big MN on the side. That's the boat. That's the one. Look, you see it's tracking. You can watch it track go down the coast. So I go to Marcia, and I say, Marcia, are you aware of this? She goes, I am aware of this. And then an hour later, she calls me up and she says, it is not tracking anymore. They turned the tracker off, and then they had to turn it back on when it went through the Panama Canal, which the other side of the Panama Canal is the Caribbean, famous for its pirates. I've been to Disneyland, and so I was like, well, if you turn it on as you go through the Panama Canal, they're going to know and be waiting. Luckily, pirates did not take the telescope. I don't know what they do with the telescope, but something. All the gold. And then it got here, and this is French Guiana in South America, where it was to be launched. I'm going to talk about this hypothetically, because you all know what the surprise of this, but maybe someone isn't aware of this, and this is going to be fun for them. But it got to French Guiana, and French Guiana is where the Arianespace, which is a French company, why in French Guiana? Colonialism. But this French aerospace company has set up this site to launch rockets, because you want to launch rockets very near the equator to get that extra oomph to throw it out into space. It got there, and this is what the site looks like, and none of us, including Marcia, were invited down there because they didn't have enough hotel room or space for us all. You know who did get to go down there? The same author of that pirate story from The Atlantic. She was down there. Reporters got to go down there because they get to take pictures that are better than mine. But anyway, it was stuck at a certain point inside of a rocket. Now, how did it get in the rocket? Well, they had to fold it up. This is one of the things that made this telescope so complicated, was that in order to fit inside of a rocket, in order to fit something the size of a tennis court inside of a space that is much less than tennis court size, you have to fold the whole thing up. So you can actually see that the mirror is folded, and then on either side, the sunshade is entirely folded up inside of this thing. So it was folded and stuck on the top of a rocket. The rocket, by the way, was sitting on a platform and driven out to the launch site. At that point, when it was driven out there, someone asked, is there like bolts to hold it onto the platform? And they said, no. If it falls over, if you bolted it, it would just take the thing over. So it's just sitting there by gravity, meaning they kind of like rested it on this thing and drove it to the launch site, which these are not great things that you're hearing in December of last year if you are a person who's working on one part of this thing. This is pictures. This is the last picture humans will ever take of a resolved picture of the telescope as it goes inside of the Arianespace rocket. Here's the rocket after it was driven out. This week, I don't know if you know, there's other very famous days associated with this week, famous holidays. We had 2 different launch delays because of weather as we got closer and closer, such that it looked like it was going to launch on Christmas. Marcia, all of NASA said they will not launch that on Christmas. Then a couple days later said they're launching it on Christmas. I sing in a choir that had a Christmas Eve service, and I'm standing outside a Christmas Eve service, and I am as amped up and freaked out as I've ever been about anything in my life. I was less nervous about my own marriage, because I knew that my wedding, at least I knew there, like, that's going to be great. This could blow up. Like, I knew that nothing would explode at my wedding. And like, here was something that I was like, that tomorrow morning, Christmas morning, something could explode and my career would be done. So I'm freaked out. People are talking with me. And a woman says like, oh, are you excited for Christmas? And I was like, well, I got a telescope I'm working on this telescope's launch. And she goes, what? You're working on a satellite? And then this woman very quickly said, it's national news, Helen. And I was very happy that someone stuck up for me, because to that woman's credit, she's come back in a week since. It's like, oh, I saw your satellite's been in the news again. It's very nice. But on December 25th, here in the Mission Operations Center, the Mission Control for Ariane rocket, they were going to launch this rocket. It was like 5 in the morning. Did anyone here watch it? I did. Oh, good. Thank goodness. It's such a cool thing that people are excited about this. But it launched. I wonder if I click this, if it actually shows the launch.
T-minus 30
and
seconds and counting.
I was sitting on a couch with my parents who were visiting for Christmas, and I was like very bleary-eyed because I couldn't sleep the night before at all, just none sleep, and like I'm on a Zoom with like a bunch of other people from the team, and we're kind of watching this thing, and I just like it's very rare that your entire life like focuses on one point of a thing that could go and like just go wrong in a bunch of ways, and like I don't know, I've seen enough rockets failing in the last couple of years from other places. I knew that they were really good at it, but like, and at this point I just start cackling, like laughing like a crazy person because this is happening. This thing is happening, and like I'm listening to the voice loop, like the actual comms voice loop of the people, and they're ahead of this, so I'm kind of hearing that things are going well and it hasn't blown up from the voice loop. But that would have been a real shocker to have them go, oh god, and then like 30 seconds later see the explosion. But it went up into space! It did it! It went out of the Earth! It left the Earth on a rocket! It went into space! And it gets better, like, oh man, look at these cool pictures of the rocket! The JWST's $10 billion, and that's like a lowball number. Like, could have blown up. There was an image, I guess this is actually the last image of JWST resolved not on the Earth, but this is the image where it pushed off from the rocket, and they had like a little camera pointing at it as it just pushed off the rocket. And at this point it starts floating off into space, and then you see the little solar panel deploy, and it just like was like, bye little guy, and it just left. It went off into space. I just think this is one of the coolest things. This is a screenshot. Some of the people I think in the screenshot are sitting in here right now, but you can see, I'm bummed that some people were like, I can't. I think it's because Stacy here is crying. People were very emotional. I'm up in the corner here. I'm going to zoom in on myself. This is me, this is my wife, this is my mom, and I'm really bummed that my wife in the moment didn't cover ears, because I've got my hands over my, or cover eyes, so I've got my hand over ears, my mom has her hand over her mouth, and my wife is just sitting here with the dog in her lap. This is Kevin, just disbelief that this was happening. So, a bunch of things happened after that. And JWST launched and got out there, but it had to unfold. And this is a process that was very, very, very difficult. I don't want to go too long, I don't have too much time, but just a lot of stuff happened. The solar array deployed first. The first thing was this little solar array deploying. Great, if it didn't deploy, we wouldn't have power in the telescope. That would have been a bummer. Next thing was that the antenna, this little antenna came. That's also great. Couldn't talk back to Earth without that thing, thank goodness. Then these pallet structures holding the sun shield, they deployed. And then it got really scary. The telescope mirror, the tower assembly rose right there. And then these arms, this little aft momentum flap, that was a cute little thing that helps with momentum on the telescope. But then right now, these sun shield covers have to release. And this didn't happen perfectly, and it terrified me, but it did in fact work because they started pulling out these arms and everything worked fine. And this right here, if there was like hundreds of single point failures you've heard about that all could have failed on all of this stuff, and it would have like doomed the whole thing. If like one of these arms didn't come out, couldn't open up the sun shield, wouldn't have been cold, couldn't use the telescope. They started tensioning the sun shield, stretching it tight, and that was like, oh my gosh, we were mostly out of the woods there. The secondary mirror deployed. We're now January 5th. Then they open up this little window thing flap on the back that helps radiate heat out from the telescopes into space. And then they got this primary mirror put into place. All this happened from December 25th to January 8th. And at that point, we had a telescope in space that was like open. And like all of this was stuff that they had documented online. And every time it happened, I just was like, I was able to listen to all of it going on. And to the public side, it was like everything was super smooth. And in fact, it was. But from the inside, when you're hearing all of the analysis and all the little tiny things, everything was so terrifying. It was just like a thing where I was at my most amped and stressed about stuff. Especially because if it did work, suddenly it would come to our time, the NIRCam time, and the NIRSpec, all the instrument folks. And if you do all this and you get this whole thing right, and you screw up the instrument, oh, that's really bad. So, this, by the way, is, I made this, I mocked this up myself. A lot of people, when they think about JWST, they see it like I just showed you. This is what it actually probably looks like in space, in that you can't see it. It's by design very, very, very dark. because it can still see space, and any extra light would be bad. And it's really brightly lit from the sun because the sun is always pointing towards this. And after it was unfolded and floated out into space in the dark like this, it eventually made its way to its orbital spot. And it's a spot called L2, which is 1 million miles from the Earth. It's a point that it orbits in this big circle like this Lagrange point 2. And it orbits in this circle like this so that the Earth doesn't block the sun at any point, which would be bad if you use a solar panel to power yourself. You wouldn't want the Earth to block your source of power. But it orbits this spot, and it managed to park itself in that spot so well, and it managed to get launched so well, that it has enough fuel inside of it for, at first they were saying, for about 10 years, but now they're thinking about 20 years.
Woo!
This is the most important thing I'm going to tell you tonight. Because the launch was so successful that instead of a mission that was designed literally for 5 to 10 years, it will probably be about 20 years. The thing that might limit it is not its availability of its fuel, but something breaking in the telescope like happens in all telescopes, which is really incredible. So at that point, we had a telescope, but the mirrors were all not aligned, and this is a very exaggerated version of that, but you can see that the mirrors aren't all pointing the way they are. It's kind of like a disco ball, which means if you were to take pictures through this, the light from this would not all bounce directly in on your cam where it needs to. So the next step was moving all the mirrors out, wiggling them, make sure they all worked to get ready to start turning instruments on. So they created simulations of what some of the early NearCam images would look like. They would look like this on the far left, which is like, you get all these little points that would be like spread out, and there'd be like 18 of them. They'd have to find a mosaic and take a big picture to find all the 18 little star images. The same star off of all of those mirrors, you know, like a disco ball, would make 18 little point sources, and you have to find them all, and then you have to like line them up like this, and then slowly focus each one of them and put them as one point in the center to move all the mirrors, and let me tell you, that's what we've been doing over the last couple weeks. These are people at the mock over the last couple weeks as we've been turning the instruments on. Stacy Alberts, who's one of the MIRI folks, she was out there early because MIRI was the first instrument to turn on. Jaren was out there. This is me. I was out there last week. Ichi Gami, who's another UA person, was out there last week. The Mission Operations Center is in Baltimore. It is it's at the Space Telescope Science Institute. This is Jaren getting ready for his like 7 a.m. shift, so it's dark outside. That's what it looks like from the outside. This is what you see when you're sitting at a panel. It's a lot of information, but it tells you important stuff about the health of the instrument and how it's doing and where all the internal parts of the instrument are pointing and stuff. It's really complicated, and the whole room is just chock full. I don't know if you can see very well, but it's just chock full of different images. And now raise your glass to the actual first image that they've shown from NearCam. This right here is not the simulation. This is the actual mosaic of the 18 star segments. All 18 of them are there. All 18 of them have been found, and all 18 of them over the last, oh, here we go, I'm gonna have to stop talking. All 18 of them have been identified. Once they took this picture, and this was a couple weeks ago, they had to go through and move each individual mirror segment a little bit and watch as the star moved after they moved the segment. And what's cool is I've seen a GIF of this where they've shown, like, you know, you just go through the images and you just see each individual star move a little bit to go, that's this mirror segment, that's this mirror segment, that's this mirror segment. And they've identified all of them. These are circles around all of the stars that correspond to which mirror segment. And while they were doing that, we took another set of images. This is probably more famous as of right now than this kind of, you know, even though this is a pretty important image, the more famous one that they released, that I never in a million years thought they would release this image because it's a very nerdy image, but they found a way to spin it. This right here is a pupil imaging lens image. I'll explain what that means in a second. But this is essentially JWST's current selfie, which is you can stick something inside of NearCam to let you take a picture of the mirror itself and its configuration itself. They pointed the telescope, and I think this star right here, like, so that was one that was in the center, reflecting off of this mirror segment, and the rest of them don't have a mirror the star reflecting off of it directly. And you're actually able to see this current configuration of the mirror. Open, with a secondary mirror locked into place. You see the support structures for that secondary mirror. You can see reflections off of other mirror segments of that same star's light. And this tells you the telescope works. The instruments work. The aligning is going great. I've seen images over the last couple weeks that I wish I could show you. Images that may in fact look something like this. But if I did, I couldn't tell you that. So I'm not telling you that. But if hypothetically those images existed, I may have seen them. And they may hypothetically have looked really cool. I assume in the next couple weeks you're going to see images like that because NASA was very loath to show off anything. I was very surprised they showed this. When we were in the run-up, they said, we're not going to show anything until June. And then they started actually saying, man, people are really excited about this telescope. We should show images from the telescope. And so they showed this, and the public has been very appreciative of the fact they've brought in on this process. They didn't freak out and go, why does it look so horrible? I thought it looked pretty. This is incredibly pretty. This tells you that $10 billion and 33 years of thought and effort and work have come together to form something that works incredibly well, and it's amazing. So the next steps are watch out for future images. We've got 5-6 months of commissioning to make sure every aspect of the telescope works. Pretty soon the mirrors will be aligned, we'll have it focused. We're about to have such an incredible era of astronomy because this telescope has worked. And I know a lot of people who thought very, very long and wrote at length, this thing's going to fail. It failed in one of the 100 million ways. We're not out of the woods yet, but I'm near the edge of the woods. So that's going to finish right there. Thank you. If you have any questions, I can answer them. Is there a traditional question and answer session? Yes,
questions.
right here.
Where are the instruments located in relation to the mirror?
Yeah, so if I...
Could you repeat the question?
The question was, where are the instruments in relation to the mirror? So on the back of the mirror, gosh, if I could go back farther, but on the back of the mirror there's a box called the Integrated Science Instrument Module, I think is what it's called. And it's where they are, which is when the light comes in off of the primary mirror, off the secondary mirror, it goes into this thing, which has a tertiary mirror called the aft optic subsystem. And then right behind there, that mirror helps focus it onto the focal plane, onto where the instruments are.
Do the instruments move to the mirror, or are they stationary?
The mirror, like the whole telescope moves as one thing. So the mirror doesn't like swivel around on that thing, the whole telescope just pivots. And so everything stays on that. So it's not a thing where the telescopes don't move, they will move if the whole thing moves. It's like having like a camera bolted to the back of your head, and as you turn your head, it stays with that, right? Good question. I'm sorry, this was like a rapid 30-minute beer-fueled version of JWST.
That's what we're here for.
Yes. Who built the mirror? The mirror was actually built by quite a few different people across the country. So you can actually trace every single one of these mirror segments has its own history of who built it and a different place. So it was not a thing where like one group built the mirror. It was not like built like, because these mirror segments are not enormous, it didn't need to be built like at a place like here under the football stadium. That's if you want one big monolithic mirror that's enormous, that's the place to go. But there's lots of places that can build with intolerance for smaller mirrors like this. Are there mirror people here? Because good on you. Yeah. If you want incredible mirrors that are way bigger, none of these small things.
So what are those mirror segments made out of?
The mirror segment, the bottom parts are made out of beryllium, mostly beryllium, which is fairly holds its shape pretty well. But the mirrors are coated in a thin layer of gold because gold light reflects infrared light super well. If you took all this gold and melted it down, you'd be like, oh, I'd be so rich. No, you just have like a golf ball worth of gold. That's it. It's just a golf ball. It's a very thin layer. Just they spray a very, very thin layer on the edges. And each mirror has the ability to be translated in multiple directions. It can be twisted and tilted and moved a little bit so that it can. We don't have to suffer an issue where we can't focus the telescope. We can do a very good job focusing because we can move every one of the mirrors super, like very, very fine, right? Like smaller, much, much smaller than like the width of a human hair in motion just to get it perfectly focused. Other questions? Lily, do you want to get a question?
There's a question from the live stream
Oh,
from
question from the live
Ronaldo.
stream.
about what is the daily life of a JWST scientist?
It depends on the scientist. So for me, right now, the daily life is just, 9 to 5. Well, I shouldn't say that. Marcia, if you're watching, it's much longer than 9 to 5. It's waking up and then you're looking at, so right now you're looking at, okay, where are we in the process of JWST right now? And there's like an ongoing list of steps that we're going through. You can also, there's like various channels that we communicate what's going on. You're thinking, what data was taken while I was asleep? What data is coming up? What data should I be looking at? What analysis do I need to do? So, for the images, like that we're looking at, we're trying to see, do those images look like what they should? Are there parts that are oversaturated with too much light hit the detector? Do they need to retake these sorts of data? If you're on console, if you're working at Space Telescope, you report to your shift a half hour early, and your job is to sit and monitor the health of the instrument, what's been going on. When they take data, they can't use the instrument unless they get the okay from you. So you sitting at the computer have to say, yes, we're go. We have wearable headsets that, they'll say like, the person in charge of everything is a mission operations manager known as the mom. There's a couple people who cycle around as the mom. So they'll say, mom to SI lead, or SI lead, this is mom on ops, which is one of the channels. Then ops, the SI lead, the science instrument lead, the person in the room who's in charge of all the science instruments. So SI lead, or mom, this is SI lead. We're about to do this, this observation. Can you get a go, from the teams? Then the SI lead will contact all of us. Near cam, are you go? Near cam is go. Near spec, are you go? Near spec is go. And then we're go to do the next step. That has to happen for every step that we do. That uses the instruments, and you just continue going through all that. Shifts are 8 hours. There's 3 shifts a day. So at the end of your shift, you hand off to another person, write your shift report, and move on. That'll happen for 6 months, and then the daily life of a near-camera astronomer, or JWST astronomer, will be a lot of waiting for data, and then analyzing data and writing papers, which is kind of like the life of most astronomers. Unless you're a theorist, in which case, who needs data? Other questions? Yes, right there. Yes, there in fact is. There's multiple potential successors for Hubble. This year, the astronomy community put together an astronomy decadal survey, which, as you might expect, is a survey that happens every 10 years, where the astronomy community does a good hard look at itself and says, what do we have money for? And what's important? And why should we be more inclusive? And why should we be better to our astronomers? And why should we be better to our graduate students? And why should we be better as a society of astronomers? This year, one of the people in charge of that decadal survey was actually here at the University of Arizona, Rob Kennicott, and there's another person named Fiona Harrison who's at Caltech, I think, in charge of it, and there was a lot of people, and they solicited a whole bunch of input, and wrote this big survey, and as part of that, a bunch of people said, here's what we think the next generation of big space telescopes could be, and they went and thought long and hard and said, actually, we kind of think that these are very ambitious, but we should probably not be this ambitious this early. We should really look at the lessons from this telescope and maybe think about making a telescope that's about this size but has a wider wavelength range that goes into the optical and the UV that would really succeed Hubble. So there is in fact a next generation. What?
JWST?
What?
Succeed JWST?
Yeah, succeed JWST, thank you. There's in fact, like in the planning right now, multiple kind of future versions of this. And then there's also other telescopes that are not this big, but will do things that JWST can't in terms of looking at surveys, and there's instruments on our planets. There's lots of different successors. This is part of an older model of NASA where NASA was like, we're going to have these great observatories, and they're going to be one at each wavelength range, and they're going to look at the universe and all work together. And now we're thinking, how can we think about astronomy not just as one, let's look at one picture of the universe, but how can we look at the universe as a function of time and a function of space and do a bunch of, so there's lots of successors to JWST, but you're totally right. People have been thinking about that for a while. Yes. Oh, you just wait. Anything else?
I have a question.
Sure.
If I wanted to learn more about JWST from you, is there a video I could find to educate me?
Yes. Before the launch, I released this video on YouTube that is very goofy, and if you liked seeing me wave my arms, there's a video of me doing more. If you did not like to see me wave my arms, my name is Tim Pickering, and No, if you liked seeing that, you can Google my name, Kevin Hainline. Hainline looks like hairline, but has an N there.
It's also on the SpaceDrafts Twitter and Facebook.
Oh yeah, and it's a video that I made with some friends in Los Angeles who worked on like a bunch of kids television, so it's real goofy. It's got some fun music. The person who did all the music is the current keyboardist for the band Wilco, who's just like friends with my friends and was like, I'd love to do this. And it's really amazing. It's got like a bunch of visualizations. I talk a lot slower than I talk tonight, and I go over what makes the telescope so exciting in more detail. It's especially great if you're like, I want to convince a teenager why this might be interesting. This is the video to maybe show them. All right. Oh yes. Sorry. I am very biased, so I'm going to give you a biased answer. There's lots of really cool things it's going to look at initially. In the first year, we're going to be looking at extrasolar planets and their atmospheres, and we're going to be looking at planets in our solar system, and we're going to be looking at these like debris disks around stars, like where like little solar systems, in other star systems, and there's lots of very cool things. But I work on a survey called JADES, which is the JWST Advanced Deep Extragalactic Survey, which is going to be one of the most comprehensive surveys of the deep, faraway universe. And in the next year or so, we'll have the farthest galaxy humans have ever seen. The farthest galaxy, baby galaxy in a baby universe. It's light leaving when the universe was like such a little guy. The light traveling across, we're going to see it and understand the history of the universe and how it builds galaxies and how it creates, how stars make more and more complicated atoms. Because we're sitting here made out of atoms, and those atoms came from inside of stars, and we can actually trace the evolution of the universe's building up of things, complicated things like carbon and stuff, with this survey. So it's called JADES. I'm super stoked for it, but I also work on it. If you had one of my colleagues, they would tell you a different thing. That's what they are working on. But it's a good question too. And so this is the thing, is you'll have to have me out for another beer-fueled one, maybe in a year or two, and I can show you even way cooler pictures. I mean, not this one, I should show you the cool picture, but way cooler pictures than just this and this. But like the real thing, the real deal stuff. We'll zoom in and look around, it'll be great. Woo! All right, thank you so much.
Thank you so much, Kevin. That was fantastic. That was awesome. Quick personal side, 30 years ago next month, I was a wee lad, prospective grad student here at Arizona, and I was sitting in Marsha Riki's office, and she was pitching me in March of 1992 about the cool things they were going to do with NGST at Stewart. So that's how far back I go with this. I'm old. Anyway, we're going to take 20, so feel free to go get some more beer. Definitely tip your bartenders.
Buy stickers.
Buy stickers and tip us too. All right. Yay. everybody, 2-minute warning, 2-minute warning. All right, we are ready for talk number 2. John Barentine talking about the Ashen Light of Venus, something from the oldest unsolved mystery. Take it away, John.
Thank you, Tim. Hey everybody, how you doing?
A bit louder.
Shout out to Kevin for being my warm-up act. Everybody, round of applause. I don't know if I can beat that, so this is actually my second SpaceDrafts, so thank you for having me back. And tonight I'm going to talk to you about something completely different. And just as a word of background about me, I am a recovering astronomer. I did that for a while. I'm now a freelance environmental consultant, and I do different and interesting things. And what I'm going to talk to you about tonight is something that I am not an expert in. At least I don't think I'm an expert, because I'm not a planetary scientist. But I know enough about astronomy, and I know a little bit about planetary science, and I'm putting that together with my other main interest, which is history, and in particular the history of science, and in particular the history of astronomy. And there is some fascinating stuff in here. So this is about something called the Ashen Light of Venus. So as the title implies, this is obviously a story about Venus. But it's more than that. This is a story about deciding for ourselves what is real. And that'll become evident as I go through this. Why I say this is about deciding what is real. Because we are constantly in our environment, we are bombarded with information through our senses. And our brains have to try to sort out what is actually happening from what may be happening but is unlikely. And that idea of perception and psychology and everything that goes with that is very much part of this story. So I'm going to make a case to you. I'm going to sort of treat this like giving an argument as a lawyer in a courtroom, because there is a mystery here. There is a crime has been committed, and we're going to have to figure out who done it. So I'm going to start by just briefly recapping something about Venus for those of you that are maybe Mars enthusiasts or some other crazy planet or X-planet like Pluto, and that's your favorite. And Venus may not be your favorite, but I'm going to try to convince you why it should be. Then I'm going to tell you a little bit about the history of this phenomenon, and from there I'm going to go into making the case. I'm going to go over the facts of the case. We're going to go over the motives, the means, and the explanations that people have come up with over the centuries to try to explain what's going on here, and in the end we'll try to get to some sort of verdict. So first I'm going to give you a brief recap of Venus if you are not so familiar about it. If you're of a certain generation, and I'm raising my hand, who was raised on Carl Sagan and the Cosmos series in the early 80s, you'll remember that he did an episode that was, I think, was titled Heaven Hell, and it was about Venus in comparison to the Earth, among other topics. And he did that to underscore the fact that our planet, which is this one over here on the left, by the way, if you're confused, and Venus, which is this one over here on the right, are remarkably similar in many ways, but very different in others. They are very nearly the same size, for example. So these are shown at about the same scale. This is an optical light image of the Earth on the left, and this is actually an ultraviolet image of Venus on the right to highlight some of the patterns in the clouds, because otherwise Venus looks pretty bland and boring if you look at it in optical light. But that's where a lot of the similarities ends, similar sizes, masses, etc. But what's going on underneath is a little more complicated. So by way of radar altimetry, so we put radar on spacecraft, they orbit Venus for a long time, and they build up this picture of the elevations of Venus, which effectively allows us to peel away some of the cloud layers and see what's going on underneath. And what's going on underneath is that it's a very similar terrestrial planet to ours, but unlike ours, obviously, well, there are no oceans for one thing. As far as we know, there's no tectonic activity, there are no plates or anything like that. Probably nothing living down there, although you might have seen the story in the last couple of years about the discovery of an organic molecule in the atmosphere of Venus called phosphine that might have something to do with life, although there's a lot of controversy about that. So it's a very different place under the clouds. It has a thick atmosphere like ours, and that actually leads to the trivia question, which is, so remember, thick clouds, heavy atmosphere, what's the average temperature at the surface of Venus? And I'm going to do these in Fahrenheit degrees because we're Americans. Is it 100 degrees, which is kind of like a reasonably hot day in Tucson? Is it 450, which is sort of the upper limit of your kitchen oven? Is it 870? Or is it 1,220 degrees? What do you think? Which is it? Who said C? This gentleman right here. You are correct, sir. 870 degrees Fahrenheit. So that's quite a bit hotter than your oven goes. So it's difficult to put spacecraft down on that surface because they tend to melt. But we put a number of spacecraft down there now, and it's kind of a hellish set of conditions. Not only is it hot, but there's sulfuric acid in the clouds, it rains acid essentially. Not a place that you would want to go spend your vacation. There are also two other important differences between our planets that I need to point out because they will have very strong relevance for the rest of the story. One is that Venus, unlike the Earth, does not have a permanent magnetic field. You can use a compass on Earth because Earth's interior, which is that kind of dense orange dark part in the center over there in that diagram on the left, the core of our planet is partially molten. So you have all of these electric charges running around in the core and the planet is spinning, and one of the consequences of that is a magnetic field occurs, and it's got this kind of peculiar shape to it. And it interacts with the solar wind, which is a stream of charged particles coming off the sun all the time. And that kind of causes this tail to form on the other side. But this is a good thing because it protects us when the sun does crazy things and launches flares at us. In other words, you should be happy that we have a magnetic field. We might not be here if that were not the case. Venus does not have that, which suggests that maybe the interior of Venus has already gone solid. It's not a molten liquid running around anymore. It may just be one gigantic crystal of iron for all anybody knows. So Venus doesn't have a permanent magnetic field, which is going to be important. The other is that Venus has no known natural satellites, unlike this planet with which you may be familiar. And its natural satellite, which is looking fine right now, by the way, through the clouds up there. The moon is shown here at scale with the size of the Earth. The distance obviously is not. But we are pretty much able to say that there are no satellites of Venus, at least down to the size of something like a kilometer in diameter. We would have seen them by now. This is also going to become important in a moment. So what is this thing called the Ashen Light that was on the title slide of my talk with that funny picture? And what is its significance in the history of astronomy? Well, here are a few artist depictions of what it is. And in short, the Ashen Light is a phenomenon mainly seen by people looking through telescopes at Venus, generally when it's in this crescent phase. And what people see is a glow coming from the night side of the planet, as if it's emitting light at some very low level. Sometimes it has some color associated with it. Some observers have noted that it doesn't appear to have any color at all. Many of them have noted that, if you can see over here on the left, the outer part of the planet on the night side, it gets a little bit brighter right at the edge, which is this effect called limb brightening. And that may be telling us something about what this is, if it's in fact real. But generally, this is a telescopic phenomenon. You have to be looking through an eyepiece of a telescope in order to see this. And it's been going on for a really long time. In fact, the first recorded description of this phenomenon was shortly after the invention of the telescope itself. This is an Italian astronomer named Giovanni Riccioli, who is, this is good PR from the 18th century, by the way. He's leaning casually against a copy of his book. You always want to be seen with your book in the background if you can. Riccioli was an early telescopic observer of the planets, and in 1643 he noted in the same book that he observed Venus on a number of occasions when it appeared to have this bright fringe around the outside of the planet. So here's the bright crescent of Venus. Venus goes through phases like the Earth's moon does for different reasons. So you have a bright part and you have a part that's unlit. And he noticed only on a handful of occasions that he saw this fringe around the outside of the planet. He had no idea what it was, but no one had ever reported any such thing before. So there's no precedent for this in history. And I can tell you that even to this very day, people are still reporting this phenomenon when they look at Venus through telescopes. You know what time it is. I'm going to keep going as long as I can here, but I'll stop in a moment. So in all of these decades and centuries since, Union Pacific thanks you for your attendance tonight. In all these centuries since, people continued to see this thing when they looked at Venus. And I'm just going to show you a couple of examples. This is William Durham, who was an astronomer, who was also a church canon in the early part of the 18th century. He lived in a place called Upminster, which is in far east London. He used to make his observations with a telescope in the tower of that very church, which you can still go and visit if you go to London. And he said, sometime around the year 1700, he said, I particularly remembered as I was viewing Venus some years ago, as one does, with a good 34-foot glass, meaning a telescope with a 34-foot focal length, when she was in her perigee, which meaning it was close to the Earth, so the crescent was very thin and much horned, that I could see the darkened part of her globe as we do that of the moon soon after her change. And what he meant by that was a very thin crescent moon. That again is going to come back as part of the story in another moment here. A little bit later into the latter part of the 1700s, I don't have a good picture to show you of the observer. This is a quote by Friedrich von Hahn, who is a German observer in far northeastern Germany. This is a picture of the tower where his telescope is located. It still stands. And these are figures from a paper that he published that year showing his observations of this faint light on the night side of the planet. And he said, often I saw with great clarity the dark part of the disk of the planet. Sometimes I believe the disk shape completely rounded, surrounded by a fine circle of light at the edge of the disk. So what's going on here? So fast forward a little bit more into the 20th century, and even up to today, people are still observing it. They're making sketches of it. They're trying to get images of it. You might think that that image over there on the left is there's the definitive proof, right? We got a photograph of it. That's actually not it, but I will tell you why it might be related to it in a minute. But suffice to say that this is still very current among people who look at Venus through telescopes, and we have no idea why. So after having spent a number of hours reading a lot of accounts of this through history, I was able to distill down 7 facts of the case. This is where we start making the case in the courtroom. And whatever the answer to this problem is, has to account for all 7 facts of the case. So number one, what we can say is that whatever the ashen light is, if it's real, it's not on all the time. And by on, I mean we can't just take a telescope out on any given night when Venus is available in the sky and look at it and see that it's there. People have spent their entire observing careers trying to see it, and they never do. So whatever it is, it seems to be episodic. People who say they have seen it have noted it on one night and not on the next. Or they would see it in the early part of one night, and then an hour later it appears to be gone. Whatever it is not steady. It's not a consistent feature of Venus. Number two, there are some very, very reliable, very well-known observers throughout history who have seen it. Some of you have heard of the fellow on the left, William Herschel, for example, or Sir Patrick Moore, who was probably the most famous English amateur astronomer who ever lived. This is a German astronomer named Johann Hieronymus Schroeder, who lived in about the late part of the 18th century. And they all said that they saw it, but I could come up with a similar rogues gallery of well-known observers who said very definitively they never saw it, even looking at Venus for decades. So there's something here that, again, is not consistent. If it was there all the time, everyone would have seen it. the fact that there are these very reliable people who said they saw it starts to lend some credibility to this being a real phenomenon. Number 3, the appearances don't seem to depend on what kind of telescope you're using or where you're located or the individual observer or what time of the night that you're observing. People have seen it all throughout Venus's orbital cycle. They've seen it on the evening side. They've seen it when Venus appears in the morning. So whatever it is, it's not some strange consequence of where you happen to be or what equipment that you're using. Number 4, the ashen light is most often seen in about the 4 weeks before something called inferior conjunction. And to explain what that is, there's a little picture over there on the left that shows the orbit of Venus and the orbit of Earth around the sun in the center. And because Venus is a so-called inferior planet, not meaning that it's of lesser quality, because it's a fine planet, trust me, but because its orbit is smaller than ours and it's interior to our orbit, it goes through an apparent set of phases. And this is something that we didn't even know about until the telescope was invented. And people struggled with this a long time, but it was one of the cornerstones of the Copernican theory, the sun-centered theory of the solar system, that explains why Venus has these phases. So inferior conjunction is kind of this center arrangement here where Venus is more or less between us and the sun. And on rare occasion, it actually will pass in front of the sun as seen from the Earth. But that's when it's closest to us and most of its night side is exposed in our direction. And so combing through centuries worth of observations, this is about 450 or so observations since the 17th century. This is just a histogram. It shows the frequency of observations of the ashen light as a function of the number of days after inferior conjunction. So these are all negative numbers. So I've left this part open and I've shaded this other half. This is the morning side. This is when Venus rises before the sun. And the left side is the evening side, where it appears in our western sky after the sun sets. So it's pretty obvious that the bulk of the observations are on the left side of that graph. And that may tell us something about what's going on here, but I think it's probably just an observer bias because it's a whole lot easier to just wait in the evening to see Venus instead of getting up early to go see it. I'm guilty of that as well, right? So that might just be an observer bias. Number 5, sightings of the ashen light seem to be sort of roughly correlated with the phase of the solar cycle. And when I say the solar cycle, I mean there's an 11-year long cycle during which the sun gets really active and it's throwing flares off on our direction and coronal mass ejections, and it's this sun over here on the right, versus at the minimum of the cycle when it's pretty quiet and it's not throwing a lot at us and it's not really doing very much. And if we look at the number of sightings of the ashen light compared to where we're at in this cycle, it seems like people saw it more around times when the sun was really active. And to show that point, so I've taken that same set of data from the literature before, but now the white bars here are by decade, and it starts in the early 1700s and it comes up to pretty much the present. And I've blocked off the different centuries with shading here. And you'll see sometimes, like here in the 1950s, when there was this huge spike in observations, it was also a time when the sun was really active. It was one of the strongest solar maxima of the last about at least 300 years. But there were other times that's what the red line is. It's a number of sunspots, so it's telling us roughly how active the sun is. But there were times in the 18th and 19th century when the sun was very active and there weren't very many people looking. Is that another bias? That's possible. Not a lot of people owned telescopes in that time. And then you notice there's a little bump here at the end of the 19th century. Planetary observing was fashionable. People were making observations of the planets through telescopes with their eyes. So they saw it a few more times. Well, all right, it really takes off after World War II when telescopes become affordable to more people in the post-war economic boom. Is it just that more people were looking at Venus at the time and more likely to see it? I think there's a lot of reflection of social changes that happened throughout this period in here, and not as much something that is definitely related to the solar cycle. But it's hard to tell for sure. Number 6, eyewitnesses report the color inconsistently. Remember I showed you a picture earlier that had that kind of yellow greenish cast to it in that one sketch? Well, what better way to represent it than with paint chips, like you're going to the paint store? How about a dull and rusty color is how William of Durham said it in 1700. A peculiar coppery hue, a beautiful golden light, a gray or faded brownish color, a soft gray light. It's getting increasingly poetic. Dark gray in color. This is my favorite. This is by an English amateur astronomer named Richard Baum, who I was fortunate to exchange some emails with shortly before he died a few years ago in his late 80s, who was an eyewitness to many of these events. In 1953, he described it as a ghastly gray effulgence. Or maybe we're starting to get a little green in here, a lighter grayish green tone, a little more so than the background sky. What would possibly explain why people were getting these visual sensations of all these different colors if it's the same underlying phenomenon? Now we're starting to get somewhere with what may be going on here. In number 7, no one has produced irrefutable proof that this is even real. And there are plenty of astronomers out there who think that this is all either a hoax or some kind of delusion or something like that, because if it were there, it should be very easy to measure. Well, as with a lot of these situations, it's complicated, and we may have been measuring it this whole time. So the right answer has to account for all 7 of those facts in one way or another. So what are some of the explanations that have been proposed for this over the years that might get us closer to the right answer? So there are a lot of ideas that I think we can completely rule out. Some of this has to do with not really knowing very much about Venus as a planet, and so they didn't know what the surface conditions were like. Back in the day, when you have limited information, you can speculate wildly, right? Astronomers still do that to this day. When we have very limited information, the craziest things get published, and you can defend that later on in your career. You can say, well, of course we have much more data now than we did before. Okay, that's fine. This is how we feel our way towards what might be true. So one of the ideas is something called planet shine, or in our case, it's called the Earth shine. Remember when I said that Venus doesn't have a large natural satellite? Has anybody ever noticed this? When the moon is a very thin crescent over here in the west in the evening, and you can see the night side glowing against the background sky. That's not because the moon is giving off light of its own. That's light from the sun that bounces off of our planet and then up to the moon and then back to us. So that's actually Earth light, which is reflected sunlight, on the night side of the moon. So it's obvious why you might gravitate towards this, right? Okay, look, there's light on the night side of the moon. The Ashen light is probably the same thing, right? Well, that's a problem because there's no large object around Venus to reflect that light. So it can't be something that's a simple analog of Earthshine. Okay, well, what else is there? How about something like an extended twilight? What I mean by that is, remember, after the sun sets over here in the west every day, for quite a while after, a lot of that light is being scattered through the Earth's atmosphere, and it's still lighting up the ground until some number of minutes or up to perhaps an hour after sunset, and then the sky finally gets dark. That's an image of Venus taken through a telescope, and you'll notice that the crescent extends way past 180 degrees around the edge. That's because the atmosphere of Venus is very dense, and it's good at scattering that light far beyond the sunset point, which is delimited by the edge of the bright crescent. So maybe something like that. And if you do the numbers, you can't quite get enough light over to the night side of the planet in order to make that possible. It just doesn't quite add up in the way that we might like. So that's 2 down. All right, well, what if there's something really reflective on the night side of Venus, and there's somehow some of that twilight is getting back to us some way? This was a serious idea as late as the 1950s, that maybe Venus is an ice world. It's like, the ice world of Hoth. It's just ice all the time because, one side of the planet is locked towards the sun and heats up, and the other side of the planet is very cold. And maybe it's surface ice, but, the trivia question earlier pretty much rules that out. So we know that it's not ice. What about some weird optical effect? Maybe there's scattered light in telescopes. You're staring at this really bright crescent, and maybe that light's bouncing around somehow in your telescope, and it looks like it's ending up on the night side. But if that were true, then every time you use that telescope, you would see the same thing. But one of the facts of the case that I told you about is that it's not always there, even for the same observer with the same setup. So we can rule that one out as well. So what about something more physical, maybe in the atmosphere? Remember when I told you that Venus doesn't have a permanent magnetic field, right? there's an effect in the Earth's atmosphere if you've ever been to the higher latitudes, or if you've ever looked out the window of a plane on the way to Europe on a night flight. By the way, get a window seat. You'll see the northern lights out the window in many cases. And what's going on here is that magnetic field of the Earth is steering some of those solar particles in particular ways through the air around the polar regions. And as those energetic solar particles slam into molecules in our atmosphere, they give off light. So these curtains of light associated with the aurora are something we might seriously consider. But as far as we know, how you make an aurora depends on having this permanent magnetic field. And we know that it's not there on Venus, so it can't be that. And lastly, maybe there's something about the surface of Venus itself that's just sort of glow in the dark. And as an example, I have a picture here of bioluminescence, of a phosphorescent mushroom. I think, once again, the surface temperature is pretty good cause to believe that that's not what's going on here either. But in the 19th century, when anything was possible, people thought, maybe it's some kind of bioluminescent organism on the night side of Venus. But we know that's not true. So instead, what are increasingly likely things that it could be? Well, one idea is lightning in the Venus atmosphere. Get a lot of lightning popping off all at the same time and scattering through the atmosphere, you might get a glow that's just barely detectable at Earth. And it turns out Venus does have a lot of lightning. We've detected it with spacecraft that we've sent around there. But again, if you add things up, you don't get enough lightning strikes fast enough, sustained over a period of time, to generate enough light to account for this. So that one's probably not right. What about active volcanoes? Volcanoes are hot. Kevin talked about thermal emission, infrared radiation. Hot objects give off this light that our eyes are not very sensitive to, although it turns out under certain circumstances we might be. And if there were enough active volcanoes on Venus, that could do the trick, right? Well, that one's a question mark. You know, there might be active volcanoes on Venus right now as we speak. We're going to send some spacecraft out there later this decade that might answer that question definitively. We cannot rule out the possibility that Venus is an active world. So we're going to put that one in the question mark category. So then more specifically, that thermal emission, that hot Venus surface under there, may be causing some of that light to trickle out through the atmosphere, in which case, under certain circumstances, we might see it. And it looks like you don't quite get enough light to do the trick, but maybe it's on that hairy edge. So I'm going to call that, we should think about that a little bit more. And then there's something called a night air glow, which is not the same as the aurora. This is something that happens in the upper ionized part of the Earth's atmosphere, and it happens sort of everywhere simultaneously on Earth. It's not very bright, but if you go to a place far from a city where the sky is dark at night, you can actually see this. And it's the result of chemical and physical processes that are happening in that ionized part of the upper atmosphere. We have measured the night air glow on Venus. We know it exists. The question is, does it ever get bright enough? This is starting to get increasingly interesting. This is more than just, maybe. This is more like, we should really interrogate this. Okay, so we're starting to get somewhere. And I have brand new results to show you that might just crack this case. This was literally in the news last week, and I could not have asked for a better time press release from NASA. These are images of Venus on the night side of the planet taken by a spacecraft called the Parker Solar Probe, which is in this orbit that takes it to these ridiculously close passages near the sun. It's designed to observe the sun, but it's got instrumentation on it that can see other things. And it occasionally flies by some of the planets in the inner solar system. And twice, in 2020 and 2021, it flew near Venus. And when its cameras looked down, these are optical wavelength cameras, right? The same wavelengths of light that our eyes see. It saw the Venus surface. These are real surface features. This is optical light. This is not infrared. This is the first time this has been seen. And not only that, I was talking about the night air glow back here, these chemical things that are happening in the upper atmosphere, and I said we detected them on Venus. See how these images kind of get bright here right at the edge of the planet? That's oxygen air glow in the Venus atmosphere. Like literally this wasn't a thing until just very recently. And this is a game changer. So the air glow is going to get an upgrade. Instead of just a, that's interesting, now it becomes, we should really seriously consider this as one of the possible explanations for this. But what if this isn't real to begin with? These are not the droids you're looking for. Could this be some weird mass delusion? And I say that in the nicest possible way. There are lots of phenomena that people deeply believe in that we just don't have any empirical proof for. And it really calls into this question of whether, are some people just predisposed to believe certain things. And when I say mass delusion, I say it in the nicest possible way. And I want to give you a concrete example of that. And it's something that you may well, if you're adjacent to the astronomy community, you've heard this story before, so I'm going to highly condense it. The canals of Mars. This could be the subject of a completely separate talk. Basically, here's what happened. In the 19th century, this Italian astronomer named Giovanni Schiaparelli, who was the best of the best at the time, he was very well known, widely recognized, used this telescope in the Brera Observatory in Milan to observe Mars. And Mars, up to that point, had not really been a focus of much attention on the part of planetary astronomers. They couldn't get very good views of it, but he did a lot of observations of Mars, and he convinced himself over the course of several months in the autumn of 1877 that what he was seeing on Mars were linear features. And he labeled these with an Italian word that is extremely unfortunate, because that Italian word is canale. And in Italian, that means any kind of sort of like a trench, like an earthwork. Could be natural, I suppose, might be deliberately constructed, but it's a very generic term. Well, of course, the American and British press translated that word as canals, and pretty soon everybody became convinced that there was life on Mars. So David Bowie was right. That's not what is going on, but by the end of the 19th century, because Schiaparelli was so well known, Mars became this beautiful, lush, Earth-like world with all of these canals that had been dug by a race of Martians whose cities in the equatorial regions were desperately parched, not unlike the southwest of 2021. You may have heard the story about the mega drought in the media this week. And so they built these canals to channel all this water from the poles down the equatorial regions. And as it turned out, none of it was true. I'm going to give a peremptory choo-choo. But it turns out that Schiaparelli was badly nearsighted and colorblind and went actually blind later in his life. And his linear features were never there to begin with. So you start out with the observation, which are these kind of shadowy markings on Mars that the press mistranslates, and the result is aliens. I can assure you that it's not aliens. It's never aliens, by the way. There are other explanations for why people thought they saw linear features, but the important point here is that once Professor Schiaparelli said he saw canals, suddenly everybody else saw canals and started drawing them. Almost as if they didn't see them, there was something wrong with them, because the authorities said he saw them. That was literal mass delusion. So you had people like Percival Lowell, who built the Lowell Observatory at Flagstaff, completely around this idea of, we're going to get to the bottom of this canal story. Well, the canal story was never right to begin with. It may not be that. What about the right information coming into the brain and the brain making the wrong decision based on what it's being fed? The eye and the brain work together to process visual information. You're probably aware of this. And that means that the brain brings all of its experience about what it has already seen when it makes determinations about the stuff that we then encounter that are new to us. So an example of this is something that's called a bistable image. You might have seen these used as examples of optical illusions, but they're not illusions. They are simultaneously the things that they claim to be. So the famous one in the upper left, is it the profile of like a candlestick, or is it two human profiles facing each other? You know, is this a rabbit facing to the right, or is it a duck facing to the left with its beak slightly open? The brain is perfectly okay with holding both of those interpretations at the same time. It picks one or the other, and if you look at it again, you see the other interpretation. It's the same information coming in through your eyes every time. The brain evaluates it, it compares it to its past experience, and it makes its best judgment on that basis. So maybe it's something like this. Maybe it's the brain getting the right information and then drawing the wrong conclusion. So, with all that, in the last part of my talk, what can we say about this? I like to think of it in context of Clue. I think it was Colonel Mustard in the conservatory with the lead pipe. You may reach a different conclusion. But let's quickly review the evidence. I've shown you all of these different examples for things that might be going on here, from very simplistic, real physical situations to perhaps psychology or even the way our brains handle visual information. And we were able to rule out quite a few of those. There's one that's a big question mark. There's one here that's a, well, maybe. And then there are at least 3 here that are pretty good leads. Are any of them solid enough to ever make a really firm conclusion about that? And that's where I'm going to leave it with you, is will this mystery ever be solved? It remains a mystery. And I know that's not the answer that you wanted to hear. You wanted to hear the right answer. This is why the ashen light remains what one writer referred to as the Loch Ness Monster of astronomy, right? People continue to see it. We don't have a definitive explanation. I will tell you that, especially with the Parker Solar Probe results and a much more plausible mechanism now with either thermal emission or the night air glow on Venus, that there might in fact be a grain of truth in this. What I can tell you is, as a phenomenon, as a collection of observations, the ashen light is absolutely real. But what it's telling us either about Venus or our own selves and how we process information about the world, I think is the most interesting aspect of all of this. So, despite not being able to give you that definitive answer that you want, I thank you for your attention, and I will be happy to take your questions. Kevin, my warm-up act.
Have you seen it?
That's the best question of all. Kevin's question is, have I seen it? I can tell you that I have been observing Venus for 35 years, and I cannot claim to have ever seen it. I have tried and tried and tried and tried, and I have never even seen a hint of it. So I tried to maintain my objectivity throughout all this, because I wasn't driven by this idea, well, I saw something and now I have to know what it was. Very good question. Go for it.
Why haven't there been observations? We've got good telescopes now. We can, block out the light of the crescent. Like, why haven't there?
So the question is, why haven't there been definitive observations about this, or something that's more objective? I said that no one has ever produced irrefutable proof of it. There are photographs that purport to be it. I showed you an image that was a thermal infrared image, and I showed you the Parker Solar Probe images that were optical wavelength light, and you could see surface features, that there's light to which our eyes are sensitive that is making it all the way through those clouds somehow. And I'm not ready to declare this case closed, but I think that fact really added a lot of weight to this. Why can't you just go and strap your digital camera onto your telescope and take a picture of this? I think the reason for it, even if the ashen light is real, is because there's a huge contrast difference between that crescent and the rest of the planet. And people have tried different approaches, like hiding the crescent behind some kind of obscuring device in the field to look at just the night side of the planet. And you still run into issues with scattered light and diffraction and all that. It's hard to completely get rid of it. There's always a possibility that someone will come up with a really great novel imaging technique that can null out all of the light in the crescent. Nobody's done it yet. So has it been captured on film or on a digital detector? Maybe, but it's not yet enough to address the criticism of the naysayers.
There is a live stream question from Candace about what about global aurora?
Say again?
What about global aurora?
What about a global aurora? Thank you, Candace. Candace was one of my classmates at the University of Texas. Global aurora, Candace is a pioneer in that. She's one of the people who has made the observation of the night air glow on Venus. In fact, she turned that into her PhD thesis. And there is a possibility that there is an auroral process on Venus, and it involves an induced magnetic field. We have a permanent field, so your compass always works. What she suggested in her thesis was that occasionally when the sun throws a really big wallop of a coronal mass ejection at Venus, that it can temporarily create a magnetic environment around the planet, and that's a way of getting the energetic particles down into the atmosphere for a true aurora like we would find on Earth. We can't rule that out. And in fact, I've been collaborating with her on this for a couple of years, and she's modeling this to try to figure out, well, how do we get the particles all the way down to the right layer in the ionosphere? Well, maybe there are protons rather than electrons. It could be. Like, that's still hanging out there as a possibility. So when I put an X over the aurora, it was only if it's an aurora like we know on Earth with the mechanism with the permanent field. If it's not, it would be more exotic physics. And that's an interesting result. All right.
We made it so far without any.
I know, right? Without the screen turning into a giant sail.
Man.
No idea. They look confused as to why it was pretty. It's amazing what it is as far as it's like
I saw that fan spinning up.
yeah.
I'll stand back.
All right. Anything else, or have I confounded you?
So you argued that maybe cameras are not seeing this because of the high contrast involved.
Mm-hmm.
But the whole phenomenon is based on people seeing it with their eyes.
Yes.
And the idea is that they can see through this contrast, and no modern cameras are capable of doing that.
That's a great question. So if you didn't hear that, the issue is, why are people reporting this with visual observations with this very strong contrast between the crescent and the night side, but a camera can't do that? One thing I learned through the course of this project, researching this, is that, and this is something that a couple of the experts have told me, is that the human eye is an incredibly underrated detector of light. And one thing that it handles amazingly well are large differences in contrast, right? Our visual system works really well in full daylight, which is vastly brighter than this space, but the human eye is also capable of detecting individual photons. So it is possible that the way our visual system evolved and the dynamic range over which the human eye is responsive to light is actually doing better than even modern digital detectors. That's an idea. I can't prove that. But again, the fact that this is so persistent and people keep seeing it is suggested that maybe there is something going on. Or again, maybe it's all happening in the back end of the visual processing in the brain. That's that right information and wrong interpretation part. So I think if there's any physical explanation to it, it might be just that our eyes are really good over a large dynamic range, which is actually bigger than a lot of even digital detectors, to be perfectly honest. All right. One more? I am so glad you brought that up. I'm so glad, and don't feel bad. I don't understand biology, so we're all in good company. The question was about, if you remember a few years ago, the social media viral phenomenon of the dress. Is the dress gold and white, or is it blue and black? And it was all based on a single digital image that was posted to. Come sit next to me by the fire kids, and I'm going to tell you about a social media platform called Tumblr that caught fire on Tumblr in 2015. And that is exactly an example of something called psychophysics. It's how we merge the physical world and the stimuli that are coming into our brains with that interpretation. And it turned out that I think it was in fact a black and blue dress, but the lighting conditions caused the response in the camera detector to render those as white and gold. And there were plenty of people in the white and gold camp and plenty of people in the blue and black camp. And some of the perceptual psychologists were saying, why can't it be both simultaneously? That the lighting was important, right? And that they suggested that if you were a human being standing there looking at it in the shop, depending on the lighting conditions, that you could have a physiological response to it, which was kind of either or. And that's, again, it really depends on the stimulus that we get, and then the brain starts to compare it to everything that it's seen before, and it comes to either of those conclusions. So even though under normal lighting conditions you photograph it and it's definitely one way, it was remarkable to see how many people said, oh yeah, it's definitely this, and the other camp said, oh no, it's definitely that. And it's just a fascinating quirk about the way we process visual information that was manifested in that example. So I'm glad you brought that up. Yes. So we probably better wrap it up there then. Thank you again. I appreciate your attention. Happy to stick around and talk about it if you like.
All right, thank you so much, John. That was fantastic. And thanks again to Kevin for his fantastic talk. So another round of applause for our fantastic speakers this month. We will be back here on March 15th for SpaceDrafts number 74. So stay tuned for the announcements for that and our lineup for speakers. Thanks again for coming. Please feel free to come up for more swag, tip us, tip your bartender, hang out, have more beer, enjoy. It ended up being a beautiful evening under an almost full moon. Cheers, everyone. Woo! Awesome, John.